So this is a short video lesson on section 8.1 titled Apply Exponent Properties Involving Products. Essentially what we're going to be doing, we are going to be multiplying exponential forms and seeing what the products look like when you multiply a set of exponential forms. So first of all, before we get started with that, you need to know what an exponent looks or an exponential form looks like and what each part represents. So this is pretty much as basic as an exponential form comes up to or comes in. So you have two very distinct values there. The first one, the large one, the x, is known as the base. And the little one is known as the exponent. Sometimes it's called the power. And together they give you the exponential form. So what the exponent does is it will raise the base to a certain power, which means whatever the exponent number is, you multiply the base against itself that many times. In this case, since x is raised to the second power, so the base is x and the exponent is 2, you multiply the x against itself twice. That's what it means. Essentially, this is the exponential form of this particular product. And the way it works is whenever you have a multiplication between a pair of exponential forms, first of all, before you do anything else, you need to make sure that the bases are the same. If the bases and the product that you're working with are not the same, you cannot go any further. You stop right there. For example, if I gave you this, and I told you to solve this, you really couldn't do anything aside maybe writing them next to each other, but you couldn't really come up with a product here because the bases are different. So in 8.1, everything that we work with relies on the base being the same. If the base is different, you can't combine the two different members of the, well, in this case, the problem. Now, so this would be just, in this case, you just put them next to each other and you're done. There is nothing else to do because the bases are different. You can't really do anything to the exponents if the bases are different. Now let's take a look at what happens when the bases are the same. I'm going to bring back that very same example that I gave you, this one, except I'm going to write down the problem in this form. Now we already know that this is equal to x to the second power, but why? Because there's a hidden 1. If there is no exponent present, there's always a hidden 1. If the base is the same, what you do to multiply the powers having the same base, you add the exponent. So when you're multiplying powers that have the same base, you just add the exponent. The base does not change. So we started out with the base x. We're going to get a base x. The only thing that changes is the exponent. In this case, we're going to add them. 1 plus 1 gives us 2. If we had something like this, a to the mth power plus a to the nth power. So the bases are again the same. And if you're, sorry, it's multiplication, my bad. So again, if you're multiplying a pair of exponential forms and the bases are the same, you're just going to add the two exponents together. Same thing if instead of using variables for the base, you had numbers. So if you had 5 to the 6th power times 5 to the 3rd power, Again, the bases are the same, so the base doesn't change. And you're just going to add the exponents together. 6 plus 3 is 8. And that's kind of the gist of what we are doing for the most part for this particular section. There's a little bit more to it. Let's do another example here. Let's say I have negative 2 to the third power times a negative 2 to the fifth power. The base here is negative 2 for both. It's the same, which means we can work with it and it will not change. What does change is us adding the exponents. 3 plus 5 is 8. That's it, we're done. Again, you're not going to multiply the bases together, even though it's tempting. You're not going to get negative 2 times negative 2 equals to negative 4. No, if you're multiplying these exponential forms and the bases are the same, you leave the bases alone and you just work with the exponents. In the case of multiplication, you add the two exponents. Let's do this one. We have y times y to the third times y to the second. The bases are all the same and we're multiplying exponential forms. We're going to put the bases y because that doesn't change. Here there is that hidden 1 that we don't typically write, but it's always there. So if there is no exponent present, assume a 1. Kind of like if it's x plus 2, there's always a 1 in front of that x being multiplied by. There's always also an exponent of 1 present too. It's the hidden multiplier, the exponent in this case. 1 plus 3, that's 4. 4 plus 2, that's 6. Let's do just one more. Example, 7 to the 6th power times 7 times 7 to the 8th power. Again, all the bases are the same, so if we're multiplying these exponential forms, the base will not change. 6 plus a hidden 1, 7 plus 8, that's 15. So that's essentially the first part here, multiplying a set of exponential forms. If they have the bases the same, you leave the base alone and you just add their exponents. So the base will not change, but you'll get a new exponent number. Either it's going to be larger or smaller depending on the exponents themselves, because the exponents can be negative. We actually didn't do any examples of negatives. Let's actually do one or two. Let me set on waste paper. We can write something like this. Let's say the base is w to the third power times w to the negative second power, because you can have negative exponents. Same base, so the base doesn't change. 3 plus a negative 2, it's the same as 3 minus 2, that's an exponent of 1, or you can just write down w because again the 1 is a hidden. What if we had, let's say, the base of 8, and here you had the exponent 4 times, again, 8 to the negative 6th power. The bases are the same. We're multiplying a pair of exponential forms, so the base does not change. But we're going to add their exponents. 4 plus a negative 6, that's a negative 2, so 8 to the negative second power. So yes, negative exponents exist, and you work them the same way that you would work any other negative number. So that was the first part. The second part talks about finding the powers of a power. So what that means is, for example, if I have this, a to the nth power taken to the nth power. So it looks kind of strange, but essentially here we are going to be finding the power of a power. When this happens, you are going to multiply the two exponents. You didn't do this before. For example, when we were working with exponential forms with the same base, you didn't multiply the two exponents, you added them together. In this case, you're not going to add, you're going to multiply. There's only one base, but you have a power of a power. So here it would be A times M times N, or A times M N. Let's take a look at it with some actual numbers in there instead of just values or variables. So if you have 3 to the 4th power all being taken to the 2nd power, so you have a power of a power. The base doesn't change again, just like before. And in this case, you're not going to add the two exponents together because you don't have 3 to the 4 times 3 to the 2nd power. You're taking a power of a power. So in this case, you're going to multiply the two exponents together. So 4 times 2, which is 12, 3 to the 12th power. Let's do another one. 2 to the 5th power to the 3rd power. Again, the base doesn't really change. The base doesn't participate. The only thing that does participate are the exponents. Here you have a power of a power, 5 to the power of 3. You're going to multiply the two exponents, so it's 2 to the 15th power. Let's take a look at another one. Let's say you have a -6 to the 2nd power, and then all taken to the 5th power. Again, the base doesn't change. The base will remain, so that don't let that negative intimidate you just yet. And then 2 times 5. Apologize for the noise. So -6 is the base, and you have a power of a power, so you're going to multiply the two exponents. So you have 2 times 5, which is to the 10th power. So let's do one more. This one we have y plus 2 all to the 6th power, and then on top of that everything to the 2nd power. Now here you need to remember that this is the base in its entirety, not the y, not the 2. The y plus 2 itself is the base. So it looks a little strange, but this is the base. So you write y plus 2, that doesn't change, the base doesn't change. And then it's a power of a power, so you multiply the two together, 6 times 2, that's 12. So you have two cases, in one where you have a pair of bases that are the same, and essentially you're trying to get the product of powers that have the same base. Then in this case you add the two exponents together. In the other case you have a single base and you're getting a power of a power, so you're taking an exponent to a higher power. In this case again the base doesn't change, but instead of adding you're multiplying the two exponents together. I'm going to post another video of me working out some of the homework problems, so we'll get a fair share of them to help you out if you're still confused. But thank you very much for watching this, and have a nice day.